Well, the big data has become a big wave, and we're very happy to have Salim as our talks speaker today. And Salim is a senior software architect at Informatica. He's going to tell us about this big data-oriented data engine platform he's leading to build on. And we also have Nalita here, Miss Nalita here. She's the global head of the talent programs of Informatica. So I will head Nalita talk a little bit.
Thank you. As Dr. Zhang said, we keep hearing the word big data, but I think pretty much everybody and his sister says that they're in the big data space. I just saw an ad the other day that Walmart apparently is in the big data space now. So I wanted to just give you like a very high level 1 minute introduction to what our organization does. We've been around for quite some bit, and I would characterize us, this is what one of our VPs says, that we are the plumbing of data. We are the folks that integrate it, that clean it up, and that make it usable. One of the sort of neat models that we predicate our business on is that we are agnostic. And so we're really a consultant trying to solve the big data problems for our clients. And one of the big problems that a lot of folks have out there in the world right now is data quality and data integration, right? Multiple platforms, multiple systems, and the global environment. So all of this impacts that problem. So Salim's going to talk a little bit about, what is that data integration problem that we're trying to solve for. And then he's going to talk a little bit at the end of his talk about sort of our next generation. He's going to start with our current solution and then end with our next generation conversation. So without further ado, I'll hand this over to Salim.
Thank you, Lolita. Hi, everybody. So the agenda today is to introduce you to the Informatica Big Data contribution. So I will start with the kind of an introduction to the big data problem. Then we'll explore some current use cases and new trends for big data usage. And then I will introduce the challenges to effectively dealing with big data and the associated solutions. And finally, I will end with the architecture of the big data, the Informatica Big Data solution. And please, you can interrupt me at any time, for asking questions. So in terms of history, big data didn't really start with Hadoop. Big data is kind of like a relative terminology. As soon as basically the hardware is overwhelmed with the data size, you have a big data problem. So in 1997, the ACM, there was like an article in the ACM Digital Library that used the big data terminology. And I think it was like a NASA paper that dealt with the data visualization, where basically local machines were overwhelmed with the amount of data to visualize. So they had to kind of and also the operating system couldn't cope with the amount of data to basically host either in memory or also on the swap. So they had to kind of add application logic to deal with that. In 2000, an article published to analyze to quantify basically the amount of data produced. And in this analysis, in this study, the accounted for the data stored on paper, on CDs, DVDs, and magnetic devices like hard drives. And they concluded that in 1999 there was roughly 1.5 exabyte, which is a billion gigabyte. And they noticed that 90% of this data was digital, was on hard drives. And like kind of follow-up on this an analysis computed or concluded that in 2002, the data has tripled to 5 exabytes. In 2001, there was like an article published by a research technology company, Gartner, and in that paper, the author used 3 dimensions to define what is big data. So they used volume, they used the velocity, the data, the speed by which this data has to be subsumed, and finally the variety, like structured, semi, and unstructured data. And to date, most of the businesses use basically these 3 dimensions to define the big data problem. In 2003 and 2004, Google released 2 key papers, the GFS paper and the MapReduce framework, that became really the backbone for the big data architecture. Finally, in 2005, Doug Kitting, while working at trying to create a web search engine, Doug is the creator of the Lucene search engine, and he was trying to kind of like come up with the distributed file system, and then suddenly he saw like the GFS and the MapReduce papers, and he used this this kind of like concepts to make much scalable web crawler and web indexer, and then built basically the Hadoop. So now let's talk about big data use cases. So this is just to kind of indicate that big data use cases existed before Hadoop. So of course we have big data being used in businesses, like the big search engines, social media, like Google, Yahoo, Facebook, in the data warehousing, like Teradata, and IBM, providing both like very like scalable data warehouses and also grid basically technology, and Walmart having already in the 90s data warehouses in the size of petabytes. Then this is kind of like known to everybody here, like in the science, the LHC producing like a huge amount of data, and only a fraction of this data being analyzed today because of the magnitude of this data. Then also the astronomy, healthcare research also generating a humongous amount of data. And something related to science is also the government, basically security, climate modeling, and research, also producing large amount of data to be processed. Now, the new trends. So what we have seen at this time is new use cases where enterprises didn't really have a big data problem. But instead, what they have seen a technology that can deal with large amount of data. So they are trying to leverage this technology. And so among these use cases, overall, it's about analysis, risk analysis and fraud detection, brand and sentiment analysis, customer insight analysis, targeted marketing and personalization, and overall business intelligence. Now I'm gonna take you to kind of like a made-up use case that I had to build with a product manager at Informatica, so that we don't really get into talking about real-life use cases. But this is like a good example of what our customers are trying to do. So first of all, let's start with the data flow concepts. So at Informatica, we allow our users to kind of we provide them with the data flow language, where the blue boxes and the origin boxes represent input and output, and the green boxes represent transformations. Basically, a transformation is like a function that can take an input relation and transform it into another output relation. And so in this made-up use case, the intent. So assume we have like a bank, and the bank wants to expose a new service, and the service is to provide daily stock recommendations. So we kind of like created like 2 steps, in order to do that. The first step is to calculate the risk and the popularity rating for every stock. So for that, what we'll use data sources from Bloomberg that provides basically the daily stock pricing, and then Twitter feeds with NLP technology to kind of like try to compute the popularity of a stock, and also the weblogs, the clicks. How many, what type of stocks were of interest to users, and with that we produce like the stock profile for on a daily basis. The second step is to generate the daily recommendations, and here we will kind of combine the data produced in the previous step and the information stored in data warehouse, the historical information. So so the first step is to kind of like join the customer activity with his or her basically past activities, like what kind of stocks, what kind of risk taking these users have exhibited in the past, and from that we will build basically kind of a profile for users. Then we will match this user profile with the daily stock, basically like risk and also popularity, and then provide every user kind of a targeted offering. So in this in the next few slides, I'm gonna talk about. Yes.
In the previous example, did you correlate the performance of the stock tips with other situations?
Honestly, this was like a made-up use case. Yeah, sure. So we did our best to just, in the end, just kind of like convey the message. But I mean, like same thing, like in the previous, like calculate risk and stuff like these are kind of abstract concepts. But the real thing here is our users are really trying to do that. For the first time, they are trying to use to parse emails, to parse basically like Twitter feeds and things like that to do something similar.
Yeah, the traders in Chicago use it for bringing weather data in to calculate commodity prices for yields, and they follow the farmers' Twitter feeds and stuff like that.
Yes.
To see how it's kind of coming down.
Yes. Trading. Basically, the space of ultra messaging and complex event processing. In this slide, like I wanted really to kind of introduce the challenges for. Gardner has published like research about big data projects. What they have noticed is 80% of the time is being spent in integrating the data, and only the remaining being used to effectively use basically the data. Like and in that analysis, like there were like multiple use cases. Like for example, I think a data scientist from Fermi saying that who get paid almost 300K to do data science, and he spent 80% of the time just scrubbing the data. And only if he is lucky, he will spend 10% really doing true analysis. So in this slide, what we'll see is conventional methodology to kind of deal with basically the data integration problem. So what you'll have data sources, which can be like OLTP systems, OLAP systems, and the target like data warehouses and also data marts for speed up. And usually ETL jobs being used, and ETL jobs, like they can run only in a certain interval. But what we have seen recently is this problem is getting accentuated because now we have way more, like much more data. We have data coming from documents, from like emails, social media, from like mobile, scientific data, and still you need the same. You have the same time frame to kind of integrate this data. And then on top of that, the user basically is kind of like being left asking, can I trust this data, right? From where this data came? Like, did it come from OLTP or it came from some Twitter feeds? So now with Hadoop is definitely contributing into addressing some of these issues, like the big data problem. But how is it being used? So what we have noticed with our partners is that Hadoop is being used along with existing system. It's not replacing. At this time, it is not replacing legacy system. Instead, like if, for example, let's say I have like data warehouse, and I need to execute some transformation logic or analysis even. I can either use system, which can cost like millions of dollars, and or I can kind of delegate some of this analysis, especially for the new type of data, for new use cases, to Hadoop. So today, that's exactly what we are saying. We're seeing Hadoop being used at the enterprise level as a complementary for existing systems. Now, I'll take you through the Informatica contributions to the big data problem. So in the last couple of years, Informatica has been pushing for the notion of virtual data machine. So we have like we have kind of two environments. One is the development environment, then the runtime environment. So what we wanted is really for our users to deal mainly with an abstraction. We didn't want them to kind of like get bogged down to the details, like, oh, am I dealing with Hadoop? Am I dealing with the cloud? Am I dealing with this system and that system, which is extremely error prone and demanding. So instead, what we are doing is kind of like asking our the data stewards to capture the physical model of the enterprise or of the data, and then let the data architect to model the conceptual enterprise model and create basically the mappings and between this physical layer and the abstract layer, and doing that completely in using like GUI-based tools. From there, the user can deploy basically deploy this the captured metadata into different scenarios. So, for example, you can do batch. You can say, okay, this is my physical model, and I want to populate the warehouse using this abstract model, and we'll generate automatically the necessary logic to do basically the ETL step. Or you might want to expose a virtualization layer where you will expose this business entities as maybe we have like a big operations to kind of so we target basically the more for agile business analysis. But what we have seen is corporations trying to kind of create really like a centralized data service layer at the core of. And same thing for big data. Our users today, with just basically like kind of like a checkbox, they can say, okay, I want to run this job on Hadoop, or I want to run it on the Informatica grid, and they will not have to, they will not see any difference in language. We'll see the same monitoring, basically feedback. Like it is really seamless, except maybe for the IT personnel, if they have to kind of maybe do some tuning, then they have to go into like log files and things like that. But otherwise, the logic is really at a high level. So this is kind of like a sample of the Informatica data flow language, where the user just used these boxes like the data sources and transformation like joiners, aggregation, and like we have like a very large repertoire of out of the box transformations. Also, if our users want to kind of create custom logic, they have access to Java transformations to basically extend the transformation list. So for the Hadoop use case, if the user wants to deploy, for example, this data flow on Hadoop, the engine at runtime for the current solution will generate a SQL statement. In reality, it's more than that. I'll talk about it later on. And then we will push down this SQL statement on top of Hive. So any question thus far? All right. So now I'll get into the underlying big data architecture. So in this slide, I just wanted to kind of contrast the Informatica data flow machine with a database. They are really kind of like similar. So we make use, instead of having a SQL query, we have instead a data flow, and internally we kind of like parse the data flow, we optimize it, we do rewrite, and then we have the ability to generate execution plans for different targets, for different runtimes. So in this slide, so you'll see like the overview of the virtual machine. So as I said before, there is a design environment. In the design environment, our users are more like kind of targeting basically services like data quality, data cleansing, data discovery, ETL, data services, and they use the underlying transformation logic. What we mean by data object is really these conceptual business entities that have been modeled, and also all of this is backed by we have a workflow language and data flow language to basically express this logic. The whole thing is stored in a deployment artifact called an application, stored in the metadata repository. From there on, the IT personnel can deploy these applications into our runtime.
Right. So why do you have both the data flow and the workflow? They're very similar.
It is similar, but see, the data flow, the data flow is all about data flowing, right? Whereas in our workflows, we can dispatch a synchronous task that might not exchange basically data. And you will see the concept of workflow being used inside the data flow engine itself. Yes, there is like a big synergy. Yes, so before I leave here, you can see here from the virtual data machine that the same data flow that one has designed, it can seamlessly get executed on top of the Informatica Grid or Hadoop without basically almost the checkbox. I wanted it, and the reason why we provided this facility is the Informatica Grid in the past has been used for for kind of medium data for medium jobs. I would say between maybe 30 to 100 nodes. Whereas for Hadoop, we do understand that Hadoop can become kind of an enterprise resource, maybe 500,000 nodes, and it will be kind of good for for us to allow our customers to use the Informatica Grid or the Hadoop Grid. So so in the previous example, I have showcased that for the current solution, we are translating the data flow into SQL, into a workflow really of scripts, and then we use an embedded Hive engine to execute our logic. Where can I see the question? Oh, I see it here. Do you have data replicated between Hadoop and Informatica Grid, or using the underlying same data? So the question was, do we need to replicate data? The answer is no. So Informatica has a very rich set of adapters or connectors, and we can basically access data from like almost any data source, like mainframe, cloud, file system. I mean, Hadoop cluster, Hadoop, distributed file system. We don't have to replicate. So so here I just wanted to kind of like summarize the Hive architecture. So Hive is the Hadoop SQL kind of like interface. It is not per se really like a database in the sense that where you can. It's mostly like for read, like you populate it with data, and then you can do like you can perform SQL analysis. But you, for example, like HBase, update individual records and things like that. So it has basically Hive has a metadata engine, which is a metastore backed by a database. Most of the time, we have seen MySQL being used, and it has a data access layer, which is called the Hive server, and it exposes like JDBC and ODBC and a thrift interface for accessing data. But internally, most of this data logic is through the driver. And in our solution, we basically tap directly into the driver for performance reasons. So we bypass completely the Hive server and we use directly the driver. Hive also exposes kind of like a set of extensions to allow us to basically attach the Informatica data flow logic. So as far as input-output, it has a notion of, this is really a Hadoop concept but extended by Hive. There is a concept of an input and output format, and also a storage handler that allows basically an application to completely take control of input and output. Then there is a concept of SERDE. SERDE is like serialization, deserialization. So we can basically attach our own serializer, deserializer, so that we can basically use different formats when we stage, for example, on the HDFS. There is also a concept of UDFs. UDFs is Hive has kind of a library of expressions, but it is quite limited. So so it has this interface where you could register for your own repertoire or of expressions. That's the reason why, like in the abstract layer, our users, they can use any expressions they want, but at runtime, when we do the translation, if Hive has a similar expression, we'll use it. Otherwise, we will use our own. Finally, for situations where we just cannot express the logic using SQL, like for example, we have seen that with our profiling and data quality transformations, where the logic is, there are algorithms that will not basically execute or cannot be expressed using a SQL. So for that, there is kind of a streaming interface where we can tell Hive, we want you to create a pipe between you, the Hive engine, and our engine, and send all the data through our engine. So there we have the ability to even extend the transformation that the transformation logic that Hive can do. So for example, we using all these extension points, we have been able to kind of offer transformation that didn't exist in Hive. And for the input and output, we have our own parser, which can deal with like a huge variety of data formats. So it has an engine that basically you can even teach it, basically like some like a design time. You can give it like samples, and it can build basically some statistical models to basically at runtime be able to do the parsing. And also it supports most of the current basically serialization formats. Otherwise, Hive, I think in Hadoop there are like very few formats that basically come out of the box. So now, more like design details about the Informatica virtual data machine. So as indicated before, it really looks like a database engine. So we have a statistic framework. Currently, the statistic framework has access only to the data source statistics, so that we can, the optimizer can basically compute appropriate execution plan. And our problem in the optimization is way harder than the database. Database kind of like host the data, so it can partition the data, it can store it the way it wants. We can't. Our data, can be stored anywhere. So that's the reason that this layer is extremely important for us. So in the optimizer, we parse basically the data flow. Then we normalize. We have we have logical concepts at the user level that, just to make the life of the user easier. But internally, we kind of like flatten the whole thing so that our machine understand kind of like a smaller set of instructions so that we can basically kind of implement and optimize. I already talked about the optimizer. We have, so instead of going this way, let me go most probably like in the next slides, which will introduce this in more details. Yeah, so in here, this is the data flow compiler. Another thing about optimizations. So not only we can rewrite the data flow, but also we can push down. So imagine, like, for example, you use a join. Sometimes the join, the two sources are on the same database. So we can basically push down the join fully to the database. Other use cases is semi-join. There is a filter, and we know that if we push the filter to the database, then the amount of data movement will be very less. So then the cost optimizer will basically when it kicks in, right? So with Hadoop, it will say, do I really want to push down to the database? Because the use case, most of the use case is to kind of try to, for Hadoop at least, try to perform the join in Hadoop, and so that our data warehouse is not utilized. So the cost optimizer will have to kind of juggle between the target environment. And finally, the execution plan. So which leads me to the execution part. So the execution plan is a workflow. And this workflow is, it's a set of scripts, tasks. And this task, they can target, the workflow can target basically in the current version, the workflow runs, like I would say 90% of the time in the target grid environment. But we are trying to change that. I'll talk about it later on. So the reason we used a workflow is to kind of like, for example, when we have multiple joins involved, for example, right? We can rewrite some of the joins as lookups. Informatica has, it's not quite, Hive has this notion of map join. It's close to it, but we have our lookup technology is kind of like way faster. So what we do, if we notice that one source is being joined into different use cases and it's smaller than the other sources, what we do, we kind of like build a bit tree. We push it to the target nodes. From there, instead of doing like a MapReduce join, we do basically a map only join. That's one use case. If the data, somebody asked me, somebody asked me about the need to replicate. So if the data is outside of the HDFS, so what we will do, we can have tasks to move the data from Hadoop to the HDFS. In some cases, like we stage it. In other cases, I talked about our integration with Hive, the storage handler concept, where in that sense, if we are, for example, dealing with a database, we can pull the data directly from the database using a configurable number of, like an automatic number of connections. And then we can also, the optimizer will decide either to stage it or to stream it. Yes.
Yeah, so for sending, normally we send all your data to relational database. Is it possible to have it go in parallel to the Hive cluster so that both have the same copies of data in real time?
So possible. The reality, we provide we provide a framework. We're not really into what the user will do with we don't know exactly how they're going to basically use our solution. So for example, they can, using the data flow, they can decide to kind of stream it, or they can decide to replicate it. And currently we have a use case, not for database, but for weblogs, where we are basically working on, where we are providing a solution for provisioning. Like we go to the web machines, web servers, we get the log files, and then we copy them onto the HDFS. Okay, so it really depends on the use case. In this use case, what you see here is like a simple script where there is like, we are reading from a source, we are performing an aggregation, then we are writing to a target. And here you see like this is kind of an ETL project. You will see like DDL to create virtual tables. What I mean by virtual tables is really they most of the time they're not backed by physical store. Like because we use the storage handler, we Hive doesn't own the storage. In other use cases, the user can deliberately create a Hive source in the data flow. Then the Hive will own basically the data. And in the next script, you see the script executing. Like we'll use an insert override that has the necessary logic to read from the virtual sources and then write it to a target. Yeah, already talked about the Hive driver. So in here, you can see that this is how Informatica has kind of like hooked into Hive extension points. So we are able to kind of like source from HDFS using our own parsers, so that when the user like uses our development environment, the user doesn't have to worry about the difference in formats, in data formats. And then we extended basically the UDFs, and we use the streaming technology to extend the repertoire of transformations. So as far as connectivity, so currently we are connecting to to data sources using like either streaming. But there are like for big data, there are also some other possibilities. Like for example, we can have it in two-step where the data can be staged in bulk, and then we can basically retrieve it for faster basically acquisition. Monitoring. So Informatica has its own monitoring tool, and what we did is to kind of when we execute the data flow, we expose the let me show it here. We expose the execution plan, and we if we used a MapReduce job, we provide basically the link to the MapReduce job, so that if users wanted to kind of understand what happened, they can like the full details, they can go to Hadoop. We are working with also Hortonworks and with Cloudera to make this integration like more seamless, because they are working on their own kind of monitoring frameworks. And finally, like I'm gonna basically take you through two use cases where one we are sourcing from a relational source, the other one we are sourcing from flat file. So the first thing here is we transform our mapping logic into HQL. Then we stream, we use our the storage handler extension point to directly read from the database, perform processing. We write we write basically the intermediary data into in this use case. This showcases like a Hive target, but the reality is, if we have another relational target, then we will avoid staging and go directly to the target. We also update, the statistics. The other use case is flat file, which is really similar. So for flat file, if it's on a remote file system, we copy them to, we stage them to the HDFS. If we have to build lookups, we will do that as pre-tasks. We'll then perform the necessary processing, and then publish basically the results and update our statistics. So this kind of like takes me to the end of the presentation. Maybe a few minutes I wanted to kind of talk about, this is the first release of the big data solution. And when we worked on using Hive as the translation engine to kind of like to access the Hadoop processing. At that time, like Hadoop 1.0 didn't allow us to extend, to expose our functionality the way we wanted to expose it as we do it natively, because with Hadoop 1.0, you had to kind of like always build on top of the MapReduce. But with Hadoop 2.0 and basically the Yarn project, which allows us to kind of hook our own application master. So what we are doing, we are kind of like we are building basically the necessary logic to hook our own grid logic, and provide, for example, fault tolerance, not using the MapReduce like the HDFS, but we will use our own proprietary logic to do that. For data exchange, we want to use our ultra messaging to communicate, and that's basically the and again, coming back to the virtual data machine, our users, they won't even see a single thing. They basically they will have exactly the same data flow logic, and whenever we release 2.0, like Informatica 2.0, they can just decide what engine to use, and either the Hive solution or the new solution. Another thing that we are trying to improve is to have to create a workflow, like improve our execution plan. Currently, as I said in the beginning, our workflow was kind of targeting always the same grid environment. So improving our statistics by getting also to the grid topology, so that when we generate a workflow, we might target different engines and different runtimes. And the goal to basically execute the data flow as efficiently as possible.
Yeah, I have a question here. You were talking about the data flow machine or the virtual data flow machine. Does that mean you're trying to sort of duplicate the business of VMware, where you want to have in as many data centers as possible. You want to have your Informatica, data flow machine or a virtual machine that sits on top of maybe a virtual machine, or do you want to? Are you competing with VMware?
No.
Or are you this strictly an offline process? So you compile all your, you're talking about an execution plan at some point. Are you selling more of a development environment where this data flow machine, by the time you are at the runtime, it has disappeared. Everything is Hadoop or SQL or.
It's dynamic. See the competition, like our competition. You're right. What they do is, apologize. First question is no. We're not trying to compete with like VMware, and we support VMware. Like we do run on VMware.
Of the level above the VMware, if you will.
Yes.
You're sort of sitting on top of VMware.
Yes.
For instance,
our goal is really to kind of like, because our in the data integration basically in the data integration business, there are two different ways to address this problem. One is hand coding. You write code. The other one is you kind of like you create so much automation, so much tooling that really like the requirement for advanced user really decreases. That's really what we're trying to kind of really work into this space. And as far as compiling, like our development, what gets produced is really metadata, nothing else. And our advantage is you can deploy an application, and at any time we can basically like introduce a patch, introduce a new binary, and we just restart the server, and we will basically generate a brand new execution plan. And I can tell you, even our execution plan is like a database. It's not even static. You can issue 2 requests, and one time, maybe we didn't have the right statistics. You can produce one execution plan, next completely different execution plan.
Thank you.
Thank you.
You mentioned before that in your answer to Oli's question that you try and reduce the need for advanced data scientists by giving tools to your clients that enable them to do advanced analysis without necessarily coding it through. Do you see that as a main problem in your customers' information CIOs and IT units? There aren't that many good data scientists out there, and it's a real problem for people to get the personnel to do this kind of analysis.
So we definitely see that. We see like at this time, especially with big data, we see like I would like the first part. I would even rephrase it. We want to kind of like empower the data scientists. We want the data scientists to spend more time doing science than doing basically like ETL and data integration. The second part is for big data, what we have from our customers, what we are seeing is the need to save cost. Like for example, in the last few years, you have seen this NoSQL database movement, right? The reason is, in the past, I worked for an internet company, and we were like dying because like every 6 months, our traffic was increasing, doubling, and the database licensing, have more cores. So the expense was just increasing. So that's what we were hearing from our users. They don't want to throw away their Teradata. They don't want to do that. But what they want Hadoop to help them. That's the second like use case. Maybe another use case, like we talked about it at lunch, is the need for metadata. So I won't say what company. This is a big company, and like they solved the big data problem. They are happy, but we've been hours, and the whole discussion was about, can I trust my data? So they were trying to access Informatica more for the metadata part than to solving the scalability problem. So that's another problem that we have seen, because applications are generating data, and things can change, and then you create a report, then you get audited. How can you trust your data? So that's another big part that our customers are asking for.
Sure, and if I could just answer this question in a different way, we actually met with a consortium that we're now part of. Google's on that consortium, Microsoft's on that consortium, Apple is. There's a number of other big brand clients that you would recognize. And the issue is that there's absolutely a shortage of future data scientists. I don't know if you all saw, but in 2012, October, McKinsey Global Institute published a paper that's quite well stated now, that there is going to be probably about an 80,000 shortage by January of 2015 for specifically this kind of talent. And so what they've done, and you may have been reading a lot about this in the papers lately, there's twofold approach to that. One is through the institutions, such as yourself, in terms of trying to upskill their community with those kinds of skills. And the second piece is the immigration piece. It's about trying to make it easier for those people that have these really sought after degrees to make it easier for them to stay in this country and to be contributing faster. So you will see that in the last 3 months, because of this push, there have been multiple bills in front of Congress about the pathways of citizenship, about the comprehensive immigration reform, because quite frankly, that's where the technical talent seems to be right now. Which is why the second piece of this is, getting to the colleges and the universities, to make sure that we're getting these students taking the right kinds of courses.
It's kind of interesting because there's been some professions which have almost gone away, like operations research, for example, that was sort of on the periphery for a long time. Now it's center stage because the optimization part requires the algorithms to do that. But you also need to have statistical understanding as well as computer science. And so it's a kind of combination of skills that are required.
Right.
So up to now, our educational system hasn't really done that integration as well as it ought to have done, except maybe in financial engineering, where the payoff is so great and there's a very rarefied breed of people that operate in that space. And historically, that's where most data scientists have ended up in Wall Street.
Well, and the number one role right now in Silicon Valley is a chief data scientist. So if you can find one, you are worth your weight in gold right now. So think about that.
and what I heard also from customers is these are not your typical big data guys, right? What they're saying, okay, we have this technology. Can we better target our users? We want really to target them way better than before, because we want to increase our revenue and decrease our cost.
Back to the skill set.
Big data to find the data now.
Well, and to be very specific, it's very interesting. One of the reasons that we were very intrigued by your CMU program is because it's multidisciplinary. It's not just CS. And I think the traditional path has been CS. Now we've got folks coming out of linguistics and statistics that have that kind of mindset, who might not have the programming. So a multidisciplinary program is really, I think, the way to go. Yeah.
So Lalita, there was one question here. Concurrent users, this is about concurrent users. Can you support on the platform any performance numbers? So yes, we do support concurrency, of course. And on top of my head, I don't have, because we support most of the Unix, Windows platforms like VMware, so numbers will be different. And also, since we target so many different use cases, we have big data use cases, we have grid use cases, we have data services use cases, we have ETL use cases. So performance for us is critical. And in another space, in the ultra messaging, I was telling basically a story about our architect when trying to basically deal with performance. He told me we used to talk about microseconds. Now they talk about nanoseconds. They have to go into the operating system. They have to bypass basically the TCP IP stack, the UDP, and things like that, just to make sure that they get the fastest response time. Then customer buys the software and run on their data center platforms, or do they run in Informatica Cloud? We have both. We have a cloud solution. I think we partner with Salesforce.com, and basically what we have seen is the small enterprises tend right now to use the cloud because it's kind of like more yeah, and but still um, our view in the future is we might see like kind of a hybrid use case. We didn't see it thus far, where you will have like maybe internally your private cloud, and then for some use cases you can target the public cloud. I think that's the long-term vision.
I think that's starting to happen right now. It's the fragmentation for very specific kinds of analysis, and then link it back to a much bigger system.
And how do you basically exactly
DevOps folks actually really heavily involved.
the accounting part, the governance part, all this. So yeah, I think that's the next generation, definitely.
And we're actually internally piloting the hybrid model. I was mentioning at lunch that it's a very unique situation because we're our own best guinea pigs. And so we pilot a lot of our products, especially the cloud products internally. And I was mentioning that, HR, they're always very squirrely about loading things into the cloud because of security and privacy reasons. And we actually have all of our HR data on the cloud, and everybody's really happy because the user experience is that much better.